Chapter 2, Activity 4, is the quotient rule. And it's another rule, much like the product rule, that we use for finding derivatives of, in this case, rational functions. So rational functions that are shown, like the ones that are shown in on the D2L lesson here that I have on the screen. Okay, so when there's a numerator and a denominator, the denominator can't be 0, right? That would mean discontinuous function, and therefore we couldn't take the derivative of it. Okay, the quotient rule is very similar in nature to the product rule. So let's go through a couple of definitions and a couple of examples of this rule here. Okay, so when given a function that appears to be a quotient, right, we can take the derivative of it by taking the derivative of the second function multiplied by the first function, subtract this time, the derivative of the second function multiplied by the first function, all divided by the second function that's been squared. Okay, that's our rule. This is the way it looks in Leibniz notation, right? So the derivative of u over v, so derivative of u times v, take away u, derivative of v, all over v squared. Okay, let's work through an example here. Okay, so we've got our derivative of x squared minus 1, 2x, and our derivative of x to the power 3 plus 1 is 3x squared. And so our derivative, according to our quotient rule, is the derivative of the second function multiplied by the derivative of the first function multiplied by the second function. Subtract, in this case, the product of the other two. Now they can be in any order. Okay, I can put these in any order. Sometimes I am a little bit sloppy here with as long as we've got the product here. And with the product rule, it didn't matter if I did the whole thing in any order, because addition, when I had added the two products, it really didn't matter much. But the quotient rule is a little bit tighter. Okay, we have to follow our formula here pretty strictly. Okay, and there's where we go with this. Okay, so there's the quotient. I'm just going to expand this. Okay, minus 3x to the power 4, and a minus is a plus 3x squared. I won't worry about the denominator, but I will collect like terms here. So I've got a minus x to the power 4 plus 3x squared, and then a plus 2x squared plus 2 all over x to the power 3 plus 1 squared. I'll just leave it at that. Okay. The quotient rule is, again, a tool, right? A good tool in order to find derivatives. The proof is given in the textbook. I'll leave that for you guys to find. There is a pretty easy to follow proof. Okay, so there is, I mean, as with all these definitions and rules and formulas, if you like, they're just not made up. Okay, there are proofs here that help us with this. Okay, so what have we got here? So this is x to the power of 2/3 over x squared plus 1. So that would be my derivative. So my derivative is going to be multiplied by x squared plus 1, subtract 2x, and then x to the 2/3 all over x squared plus 1 quantity squared. Don't forget that important part here. Okay, let's try and get this going here. So let's 2/3 x squared. Okay, x squared as a rational with 3 in it is 6 over 3, so that'll be 2/3 x to the 5/3. Okay, plus 2/3 x to the negative 1/3. Okay, and then a minus. There's another 2x to the 5/3 all over. Okay, so we've got 2/3 minus 6/3, so 2/3 minus 6/3 is minus 4/3 is my coefficient, x to the power of 5/3, plus 2/3 x to the negative 1/3 all over x squared plus 1 quantity squared here, and that's okay. Maybe how far I could go. Okay, I could factor out I could take a greatest common factor out. Okay, this is going to be something we're going to work on over the next little while here, but I want to identify, okay, this top term, just take a second now and identify greatest common factor. In this case, I'm going to take out, okay, a greatest common factor of 2/3 x to the negative 1/3. That's this whole, okay, expression here. When I take out, okay, a negative exponent or negative power, the whole constant or coefficient, that is going to mean my last term or my second term is going to be a +1. It's all going to still be over. Okay, now what am I left with? When I divide negative 4/3 x to the power of 5/3, divide by 2/3 x to the power of negative 1/3. Okay, so will I do my negative 4/3 divided by 2/3. And negative 4/3 divided by 2/3, okay, is going to be a negative 2. And then I subtract 5/3 to get my term or my power, x, okay, is going to be 5/3 take away negative 1/3. So 5/3 take away negative 1/3 is 5/3 plus 1/3, okay, or 6/3. That would be x squared here. Okay, and that's our greatest common factor out of here. Okay, this was one we did yesterday, and we used the product rule, right? I used the product rule like this. Now I'm going to do it with the quotient rule, okay? And to demonstrate, okay, exactly, okay, just why you use the quotient rule. Okay, so the reason I'm showing this, and we did this question by product rule yesterday, because it just shows the one tool, how I can use the one tool. But then the quotient rule, how can I approach this in the same question in a different way, okay, and use a different tool in order to get the same derivative here, okay? So I've got products here, x minus 3 over top of x plus 3. I'm going to use my quotient rule after I find the derivative, and then the application of my quotient rule. This derivative first, multiplied by the second function, subtract the first function, and then the derivative of the second, all over, okay, x plus 3 squared here. And you may remember this one from yesterday. And you start to see that, yes, in fact, we do get the same derivative here. Now, I mentioned earlier the proof of the quotient rule. Okay, the proof of the quotient rule is based on a question like this. Now, again, a proof is not shown or demonstrated with a particular question example. Okay, but the concept of proving the quotient rule, okay, is based on taking the denominator, moving it up, okay, to the power of -1, right, and then doing a product rule on it, and noticing that, okay, when I do that, okay, this is the kind of expression I get as a derivative. Okay, find the point on the graph where the tangent line is horizontal. Where our tangent line is horizontal is when our slope is 0 here, okay, or when y prime equals 0. So I need to find the derivative, always, okay, with any types of application questions in this course and in this particular, okay, section. It's always best to just find the derivative, okay, and realize that that's probably where your question's going. Okay, so we know how to find the derivative using the quotient rule. Okay, let's expand. I'm just going to take a second and check my solution. like I'm frozen. Again here, just 1 second. Okay, so I've got x to the power 4 plus 3x squared all over 1 plus x. Okay, this is my derivative. Okay, so I want to find out when this expression is 0, okay, for this horizontal tangent line. Well, this leads us to another important concept in this particular section. When our derivative as a quotient, let's say, right, okay, is equal to 0, then I can focus just on the numerator equaling 0. So I can just grab this expression in my numerator and set that equal to 0. Okay, now I can solve. Okay, so I'm interested in x equals 0 over x squared plus 3 equals 0. X squared equals negative 3. This doesn't exist. There's no solution here. Okay, but here's our point here. And find the points. So if I find the points on the graph where the tangent line is 0, the tangent line 0 at x equals 0, and I should actually find it as a point here. And I think that original function was x to the power 3. Okay, so it looks like it's 0. So at the origin is where the tangent line is horizontal. Okay, there's what we've got. Okay, good application question of the quotient rule here. Okay, so take the derivative using the quotient rule, set it equal to 0, and solve for x. Okay, another one. Let's determine the equation of the tangent. Okay, at the point x equals 0. First thing, let's find our y value when x equals 0. We're going to need a point here, right? Okay, so when x equals 0, I've got derivative 1, okay, or 0. Okay, so my point's going to be 0, 0. All right, let's find y prime because I know that's going to be my slope, and that's what I need here. Okay, so I'm just going to go to the margin here, 2x, and then x plus 1. I just need my little tool here, my little crosshairs to get this. So the derivative is going to be 2, and x squared plus 1. Take away 2x times 2x all over x squared plus 1. Okay, let's do the make sure you don't cheat here. Okay, let's do the full derivative. Okay, calculate the derivative because this is the statement. It's going to be true. I'm trying to find y prime. That'll be 2x squared plus 2 minus 4x squared. 4x squared plus 1 squared. So now I've got negative 2x squared plus 2. Okay, I want to find the value of my derivative at 0. Okay, that'll be that looks like it's going to be 2 over 1. Therefore, my slope is 2 at my point 0, 0. Okay, so my slope is 2 at my point 0, 0. Gives me just simply the line y equals 2x. I've got a Desmos link here, so I'm going to show this in Desmos. I think it's time we go to Desmos. So I'm just going to pause this for a second. And okay, so when I open up Desmos and graph this, I graph my original function. Okay, I'm going to plot my point, and then I graph my tangent line here. And notice, as we thought, good to see that it's confirmed with Desmos, okay, that tangent line, okay, y equals 2x, does in fact touch the point at 0, 0 on the function. All right, we're rolling along here. Let's see what else we've got to do. Okay, we've got, okay, a variety of examples here, quotient rule, an explanation of my function. There's some more examples. Okay, should be comfortable with either way, u and v. Okay, Leibniz notation. Okay, Lagrange notation for. Okay, there's a summary both. Okay, I think we've got one more question to do here. Okay, and try that. Okay, so let's get on to our last question. And take a look at this. Consider the position function and find the moment of time when a particle is at rest. All right, so we need to find, when the derivative, is 0. Okay, so let's set this up. T squared plus 1. Our square root of t, will be that derivative. Okay, so now I can find s prime at t. I know that's going to be v at t. Okay, and that'll be 1/2 t to the negative 1/2 t squared plus 1. Take away square root t. Okay, a little bit sloppy. I'm mixing negative exponents and square root signs. That's okay. I'll clean that up when I get down here to the bottom. Squared. All right, let's multiply this. Okay, so I've got 1/2. Okay, t to the negative 1 times t squared here. I'm going to distribute in here. So I've got 1/2 t to the 3 over 2. Okay, and then I've got a plus 1/2 t to the negative 1/2. And then I've got a 1/2 and a 1. Okay, so that'll be a negative 2. Okay, t to the another 3 over 2 here. That's going to be all over t squared plus 1 quantity squared. All right, can I clean this up? Okay, sure. I've got 1/2 minus. Let's take a look at my coefficients. Collect my t to the 3 over 2 term. So that's going to be a 1/2 take away 2. And take away 2 is like taking away 4 halves. Okay, so I'm going to have negative 3 halves. T to the negative 3 over 2 plus 1/2 t to the negative 1/2. And that's all over t squared plus 1. Okay, and I want to find out when this is 0. Okay, so remember this concept: when my slope function is 0, means that my numerator is just 0. Okay, so now I have to solve for t in this expression. Okay, I can do this in a variety of ways, and students do it. And I show, at this point, I show students how to calculate or solve for t in a variety of different ways. There are 2 ways I can do it. Okay, first of all, I can set up a common ratio. I'm going to do it this way. Okay, so if I set up a common ratio, I'm looking at 2 terms here. I'm looking at this term and this term. Now, the term that's negative, I'm going to move over to the right-hand side of my equation. Okay, so my line here can become this. Okay, now I can set up again a common ratio and solve for t. Let's go 1 over, and I can go t to the 1/2 over equals 3. Okay, t to the 3 halves times 2. I can cross multiply. 1 times 2, and then 3. Okay, that'll leave a 2 here, and that'll leave a 6t. Okay, and then I add my exponents. 3 halves plus 1/2 is 4 halves, or 2. Okay, that allows me to solve for t squared. 1/3, so 2 divided by 6 is equal to t squared. That's 1/3. Okay, or t equals plus or minus. Okay, or in this case, I think I had a restriction on my domain. Yeah, t is greater than 0. Okay, so my solutions would be t positive. Okay, I'm just going to evaluate my root. 1 over root 3. And I think I left it there. I don't think I got an approximation answer. Okay, I don't think I wrote that as a decimal, so that's my solution for this one. Okay, now there is another way to do this. Okay, there's lots of other ways you can do it. Okay, I can also factor. Okay, if I factor, okay, I'm still working on this expression. Students like to factor at this point. Okay, so let's factor. Let's solve this by factoring. And again, I showed you this earlier in the question. Let's factor out 1/2 t to the negative 1/3. Leaves me with a +1 in my last term. Okay, but it also then, okay, leaves me with a negative 3 t squared here in this term. Now I can check that by multiplying, right? I can confirm that that is my term, but if I divide negative 3/2 t to the 3/2 over 1/2 t to the negative 1/3, I'm left with negative 3t squared, this term right here. Okay, so now if I factor, I've got products, and negative 3 t squared plus 1 equals 0. Okay, so I go and try and solve for t now in my two cases here. Okay, well, I don't have a solution for this one. 1 over the 3rd root of t equals 0. Okay, there's no solution here. Okay, in this expression where t equals 0. Okay, can't solve that. There's no way that that fraction is ever equal to 0. Okay, the next one is negative 3t squared negative 1. T squared equals 1 over 3. Okay, and then t equals plus or minus 1 root 3. Okay, and as we saw in the last, that's because t is going to be greater than or equal to 0. Okay, so this gets confirmed here. Okay, this answer by whatever method of solving you want to go through, just a different way to approach it. I've seen students even multiply everything by a cleaner function as well too. You can multiply. A third method of solution is you could multiply everything by a constant term here, or change the variable if you like. Okay, and that's I think we multiplied everything by 2 t squared. I get that pretty clean here. Okay, that's probably it for quotient rule. Yep, some homework questions, and good luck.